everyone, so welcome to our first lecture video in Math Stats. This is an introduction to probability. What's probability all about? So in this video, we'll talk about the definition and some notation for working with probabilities. We'll also talk about random experiments, random events, how we use them to distinguish the outcomes of some random situation. We'll talk about the axioms of probability, so what makes a probability, and we'll start working with some probability situations. So let's jump right in with a definition of probability. Probability is just a long-run likelihood that some event occurs. So over not just 10, not just 100, 1,000, but over potentially infinite random trials, how likely are each of the particular outcomes to happen? That's our probability. We denote probability in a functional way. The probability of some event A occurring is P of A. Each of these random trials, so each time a random variable is tested or observed, we refer to that as a single experiment. These experiments are the observations from completely uncontrollable or random situations. We know what can happen, but we don't know ahead of time what will happen. Each of the outcomes of these experiments we then refer to as events, so the possibilities for what could happen in the experiment. Now, events can be determined simple or compound, depending on, how complex the event itself is. So we refer to a compound event as an event with multiple outcomes in it. Suppose we're rolling, for example, a 6-sided die. Rolling a 1 or a 2 would be a compound event. A simple event then contains just a single outcome. We refer to the list of all possible outcomes that can occur as the sample space, which we usually will denote as omega. So, in discrete world, or if we're looking at what's called a discrete experiment, we're in a situation where we can list all of the possible outcomes and their corresponding probabilities, one by one. So discrete sample spaces can be either finite or countably infinite. The main idea here is that there's only a small subset, relatively speaking, of events that can occur. So for a discrete experiment, these compound events are collections or sets of the points within the sample space. So let's take a look at an experiment or a simple example coming to us from gambling, rolling a 6-sided die. You'll find throughout the semester that most of the canonical or classical probability examples are from gambling. The early probability theorists had a bit of a problem. So, consider a single toss of a balanced die. We've got some events here that could occur. Event A, for example, is observing an odd number. We'll call event B observing a number less than 5. We'll call C observing a 2 or a 3. So here's an example of what this sample space could potentially look like. So event A, observing an odd number, we have a 1, a 2, or a 3. B, this should say observing an even number less than 5. The only two even numbers less than 5 are 2 and 4. So B is that blue box. C, 2 or 3, is kind of the green diagonal box. The compound events are A, B, and C. They each contain multiple individual outcomes. The simple events are the 6 faces of the die themselves. Rolling a 1, rolling a 2, all the way up to a 6. Let's take a look at another example. So for those of you who like pineapple on your pizza, you might like this example. If you don't, bear with me. Let's take a look at the case of P's Pizza Place. So P likes a good theme. All of the possible toppings that are available at P's Pizza Place start with P. So you can get pizza with pineapple, pepperoni, or peppers, or any combination of the 3. Let's list the sample space omega, so get some practice listing the possible outcomes in a random experiment, and then find the probability that the next pizza that we order has 2 toppings. So here is the list of all of the possible outcomes. And since we only have 3 different toppings that we can choose from, the list is fairly small. It turns out that there's 8 pizzas that you can order from Pizza Place. You can get a pizza with no toppings. You can get pizzas with the 3 individual toppings. You can get pizzas with 2 of the 3 or all 3 together. So that's how we arrive at the list of 8. So then the probability of choosing 2 toppings, there are 3 ways that can occur: pineapple and pepperoni, pineapple and peppers, pepperoni and peppers, assuming that all 8 of these pizzas are equally likely to be ordered by a customer. The probability of 2 toppings is 3/8. So let's think about what probabilities need to have, or what properties a probability needs to have. We call these properties the axioms of probability, and there are 3 of them. So we'll let A denote the probability of event A occurring. The first axiom, or the first law that a probability has to satisfy, it has to be bounded. Probabilities must range between 0 and 1. On the lower end of that range, 0, that represents an event that could never happen, something that will never occur. For a 1 on the other side, that's an event that's guaranteed. An event with probability 1 will always happen. For example, something in the sample space must always happen, which leads us to axiom 2. If you take the probability of all of the simple events in the sample space, so all of the possible simple events in our sample space omega, add those up, must be equal to 1. Something in the sample space has to occur. Finally, axiom 3, if A1, A2, and so on form a sequence of what we call pairwise mutually exclusive events. So these are events that may be compound but do not overlap. There's no shared outcomes in 2 events. If that is true, then we can find the probability of event A or event B, event A1, or event A2 or event A3. That's the union symbol for those of you who maybe don't remember set notation as much. Don't worry, we'll cover it in the next video. But if we take those probabilities, want to find the combination or the overlap of these, we can just add up all of the probabilities. So those are the 3 axioms, or the 3 laws that probabilities need to satisfy. So let's take a look at how we might apply those 3 axioms. We have a manufacturer who has 5 supposedly identical computer terminals that they will ship to a customer to fulfill some order. However, unbeknownst to the manufacturer, 2 of these terminals have been damaged and are defective. An order comes in for 2 terminals. The manufacturer doesn't know that some are defective, fills the order by selecting 2 of the 5 at random. What's the probability that we might have an unhappy customer? So let's start by listing the sample space. So our sample space has 10 elements. Here I'm going to represent each terminal with a letter, so first terminal letter A, second terminal letter B. Without loss of generality, we will assume that A and B are the defectives. So let's think about the probability that the customer is really upset. The customer gets their order, both of the computer terminals are defective. Looking at our list of possibilities, there's only 1 time that occurs. That's the first row in this table. So the probability that the customer is incredibly unhappy, gets 2 defectives, is 1/10. Let's look at the probability that the customer is a little less unhappy, but still not satisfied with their order. What's the probability that at least 1 terminal is defective? Now remember, A and B are the defectives. So if we look through our table of outcomes, or our sample space, there are 7 possible ways that can happen. So there's still a 7 out of 10, or a 70% probability that the customer will get an order with at least 1 defective computer terminal. The probability that the customer is satisfied that none of the terminals are defective is down here. There's 3 ways that can happen out of 10 possibilities. Let's take a look at a more algebraic example, again working with these axioms of probability. We have a random experiment with 3 possible outcomes, A, B, and C. We'll let the probability of event A be denoted P, probability of event B be denoted P squared, probability of event C be denoted 2P. What is the value of P that makes this a valid probability distribution? Well, those axioms of probability do bound us a little bit. So P has to be between 0 and 1 because P represents the probability of event A itself, so we have that first bound. Second, we're assuming that A, B, and C are mutually exclusive, cannot both happen at the same time. So if we add up their probabilities, we must get 1 because they complete the sample space. So now using a little bit of algebra, we'll take P for event A plus P squared for event B plus 2P for event C. Add those together, combine like terms, we get the following quadratic equation. P squared plus 3P is equal to 1. Using our quadratic formula, we get 2 solutions for P, one of which is negative, so we must choose the positive solution for probabilities. So the probability of event A must be about 0.3. Probability of event B is then 0.09. Probability of event C is about 0.6, 0.61. If you add those 3 probabilities together, you get 1. The axioms are satisfied. So in the next video, we'll cover a little bit of set notation and we'll talk about some rules that probability distributions must follow. Have a good day.